This lecture is to talk about the inverse normal distribution, and we are going to start by discussing the relationship with the inverse normal and the normal distribution. So let's first of all discuss the fact that when you talk about the normal distribution, we're going to talk about the standard normal distribution at first. We want to find the probability which is this value over here, and this in a regular function is what we would call a y value, right? And we're going to start by inputting an x value, and that's the standard normal random variable that we're talking about, some value here. And this is what we want to find out, the probability. So just as with any inverse function, an inverse function works backward, right? So a regular function, some f of n, right? You start with an x, and it pops out a y. But if we talk about f inverse functions, right, the inverse of f of n, then we start with the y's and we pop out the x's. So the inverse normal distribution, this works just the exact same way as any other inverse function. It starts with the y values, and it's going to spit out the x values, sorry. It starts with the y and it's going to spit out the x. Well, our y value is a probability. So it's going to start with this probability here, and then it's going to work backwards and it's going to spit out this z value here. And so that means that we're going to be looking for this value right here when we've been given this value right here. So that's what this inverse normal does. Now, in terms of what we really want, we don't want a z most of the time. We don't have standard normal random variables. We have random variables that are distributed with some x distribution, right? X is distributed normally with some mean and some standard deviation. The z, remember, that's distributed normally with a mean of 0 and a standard deviation of 1. So we want to transform this back into this. Now, in the last chapters that we'd studied, we had been taking x's and transforming them into z's, right? And a z-score, to transform an x into a z, you take the x and you take away the mean and you divide by the standard deviation. Well, we can work backward from that transformation to get an x by taking the mean and adding the z-score times the standard deviation. And all that is just simply solving this backward. So we're going to first of all start out with a probability. We're going to use the inverse normal to give us a z-score, and then we're going to unstandardize the z-score to give us back the x-score. And that's the process that we're going to be working through. Now, these diagrams here are kind of to help us to realize that if we're using a negative z table, how we're going to be doing that. Remember that tables only give us the z table only gives us the negative z table, only gives us tail values. So if I'm looking for a probability of an x being greater than an x, or a probability of an x being less than an x, where this one here is above the mean, and this one over here is below the mean. So in terms of thinking about the standard normal, the x on the left side over here, the one that's above, would be a positive x, and this one would be a positive z, and this one would be a negative z because it would be below. If we're doing either of these two probabilities, our probabilities, these things, are going to be less than half the distribution, right? Because in terms of a picture that you see, the z-score over here, you're going less here, it's going to be less than half this distribution. Or if you're over here on this side at a positive z, right, you're looking for something greater than this, again, you're less than half this distribution. So if our probabilities are less than half of the distributions, then what we're looking at is to do a direct table lookup, no matter which one we're looking for, the positive z or the negative z's, and we just use our common sense to know which is which. Now, if I'm looking at a probability that's more than half of my distribution, like this one here, or if I were at a negative one and looking up this way, then I'm going to have to go the opposite way, right? Because if I know that this probability is, say, 0.72, I can't look that up in a table. That doesn't exist in a table. What exists in my table is this over here, which is the complement of that. It's 1 minus 0.72, and that would be 0.28. And so this is what I would look up in my tables in order to find the x or the z that is associated with this. So anytime my probability of an x being less than an x and the probability of my x being greater than an x, anytime those are greater than a half, then I have to do a complement idea on the probability in order to be able to use the inverse normal. And then finally, when I'm within two values, right, and the ones that we need to be able to do this within is two symmetric ones, or it's impossible for us to do. In those terms, our tables don't give us what's between values. It only gives us what's over here in the table. So this last one is saying that we have to make that adjustment to give us what's in the tail. So if we know this is 0.68, for instance, right, then we can't look up 0.68 in our table. We have to look up what's over here. So we know the entire distribution is going to be 1, and so if we multiply or subtract that, what we now have is what's in this tail and what's in this tail. So if we divide that by 2, then we'll find out what's in just our single tail. And so that's when we're looking between two values, like it says here. So with that said, now let's go ahead and look at an example really quickly, and then I'm going to let you guys do a couple of examples on your own to see if you've got the general idea. So I'm told that human gestation periods are approximately normally distributed with a mean of 268 days and a standard deviation of 15. And so I'm wanting to find the gestation period that represents the lowest 4% of births. So I'm going to start with a standard normal, and I'm going to be looking for the z-score over here, and I know it's a negative one because lowest 4%. What that tells me is it says that this probability is 0.04 of being in this tail, and 0.04 is in the left tail. I know that because being less than that is less than 0.5%. It's got to be a lower tail. So the probability that my z is less than this negative z is equal to 0.04. Well, remember, the probabilities that I look up, those I find in the tail of in the tails of my distribution. So tails of my distribution, I have to go look this up in the body of the table. And then I'm looking to find this value here. So I'm going to start by going to my table. So let me switch over to my table, and I'm going to look up for 0.04. So 0.0654, here's 4s right here. So I'm going to use these little lines to hone in on the 0.4. 0. So here's one that's really super close to this, and then right next to it is another one. So this value that you see right here, this 0.0401, that's close, and then this one right over here at 0.0392, that's as close as well. The 0.0401 is 0.0001 off. Let's take a look at that. That's 0.0001 this way, and the other one is 0.0008 off from our 0.0400. So this one is closer, the one that's the 0.0401. So now what I want to do is I want to follow this back to here and follow it back to here, and I see that my negative z that I'm looking for is approximately and that value is approximately negative 1.75. And that's just an approximation that it'll do for us. Now, I don't just need that value, I need it to come back to the number of gestation period days. So that means that I have to do the transformation back to an x. So back to an x, I'm going to start with 268, and then I'm going to add my z-score, negative 1.75, which because it's negative, right, it's going to take me lower than 268, which we know this is below the mean, and I'm going to multiply that by my standard deviation. So let's do that quickly. I have 15, and I'm going to multiply that by, let's see, 1.75. Now, my simple little calculator here on my computer doesn't have a negative sign, so I'm going to subtract 268, which is going to give me a negative number, but it's the same positive number I need. So that's going to give me 241 days at 0.75. So I'm going to round that off to approximately 242 days or 41 days. And if I don't want to overshoot it, I should just go to 241 days, because 242 days would actually overshoot and we'd be getting closer to here, right, which would be putting more area under the curve than I actually want to. So I'm going to undershoot it a little bit, and I'm going to leave it at 241 days. So that's how we work the inverse normal. Now I'm going to go ahead and I'm going to switch back to the other example here. I'm going to read it to you, and I want you to try it on your own. And I'll come back and I will do another lecture on this same thing. So the number of years before replacement is necessary for a specific brand of CD player is approximately normally distributed with a mean of 9.4 years and a standard deviation of 4.2 years. Find the length of time in years that represents the cutoffs for the lowest and highest 17.5%. All right, so you guys go ahead and do that on your own.